Hello, and welcome to the Society of Critical Care Medicine's iCritical Care podcast. I'm your host, Dr. Elizabeth Mack. Today I'll be speaking with Arthur Slutsky, MD, on the article Personalized Ventilation to Multiple Patients Using a Single Ventilator, Description and Proof of Concept, published in Critical Care Explorations. To access the full article, visit ccejournal.org. Dr. Slutsky has served as Vice President of Research at St. Michael's Hospital and is Professor of Medicine, Surgery, and Biomedical Engineering at the University of Toronto in Toronto, Ontario, Canada. Welcome, Dr. Slutsky. Do you have any disclosures to report?
Thanks very much, Elizabeth, for that introduction. There's nothing specific to disclose on this article. I do consult for a couple of companies in relation to ECMO. That's Baxter and Xenios.
Thank you so much. Art, do you mind describing the one ventilator, two circuit or bag-in-the-box model in which there's no contact between the individual circuits for the audience?
First of all, there's no individual contact on the inspiratory side of the circuits. There is on the expiratory side. I would suggest that anybody listening to this, it would be best if they could pull out the article and look at the figure, because I'll explain it, but it is a little bit complex and it's a lot simpler to understand if you have the figure sitting right in front of you. Essentially what this is you have a ventilator that operates in the pressure control mode, and it essentially ventilates, not the patients directly, but it ventilates two bag-in-the-box systems. It could actually be more than two, but for this experiment, for proof of concept, we use two. And I think the best way to think about this is that each bag-in-the-box system is a ventilator for an individual patient. And if we think about this, if we start sort of in the exhalation phase, usually think of the inhalation, but think first of all in the exhalation phase, the patient has got a breath, the patient exhales through the expiratory circuit, and it goes through a PEEP valve, the flow goes through a PEEP valve, then goes to a T, and then enters the ventilator about the same location as the exhaled gas from the other patient does. So that's where there's a connection. There's a connection on the exhalation side. During the exhalation, what's happening is each bag in the box is being inflated by fresh gas from a separate fresh gas flow. So each circuit would have its own fresh gas flow, which would be a blender. So you can get, the key here is that by having its own blender and own gas supply, that it's possible to have the FiO2 for each patient completely different. You could have room air for one patient, you could have 100% oxygen for the other patient. So that fresh gas flow is flowing all the time. It enters during the patient's exhalation, it now enters the bag, and it's filling up the bag for the next inhalation for the patient. So during patient exhalation, the bag is being filled up, and at end exhalation, the bag is full or partially full, and inspiration starts. The ventilator starts inspiration, generates a pressure. That pressure goes to, and the flow goes to the two bag-in-the-box systems. And it then, by increasing the pressure in the box, and there's a compliant bag inside there, the bag starts to empty and enters the patient's lungs. And obviously, each system is completely separate. So in this way, by adjusting the flow rate of the fresh gas flow, you can set the tidal volume for that individual patient. So for example, if you're using a respiratory rate of 10 breaths a minute and the flow is, let's say, 3 liters a minute, you're going to get roughly a tidal volume of 300 mils in that one patient. The other patient can have a gas flow that's 10 liters a minute. I mean, we wouldn't want to use it that high, but it can be as high as you want, essentially. So each patient now is getting their own tidal volume that's different than the other tidal volume of the other patient and not affected by it in any way. On exhalation, again, now the flow leaves through the expiratory side, the expiratory limb. Each circuit has its own PEEP valve, so you can set the PEEP individually in each patient, and then flow on exhalation goes through again through the ventilator, through the exhalation valve. I should point out they are not completely independent. At very high flow rates, because the flows are coming together and going through the exhalation valve of the ventilator, there can be some equivalent to auto PEEP, if you like, because there's this flow. So the PEEP, the flow on one circuit can impact the PEEP a little bit on the other circuit, probably a couple centimeters of water, but it's not completely independent. But bottom line is, by filling the bag and emptying the bag, you can now have FiO2, as I said, that's different for both patients. You can have a tidal volume that's different for both patients. Irrespective of the lung characteristics, the compliance of each lung doesn't really matter. And you can have a PEEP that's essentially, it is different for each of the patients. I know it sounds kind of complex. As I said, it's a lot easier if you look at the circuit diagram. I think it becomes a little bit clearer.
So, Art, if you don't mind, please share with us what inspired you to do this interesting work. Obviously, it's very topical and relevant during this time of the COVID-19 pandemic, but would love to hear what inspired you.
It's well, what inspired me was the people around me. To be quite honest, Jay and Joe Fisher and other people on the paper did the work. So this was not Art Slutsky doing everything. Quite the opposite. This was all these people doing the work and everybody coming up with innovative ideas. It was triggered. This some people have thought about something similar in the past, but there's no question that this was triggered by the pandemic, by the concern that we're not going to have enough ventilators. I have a number of colleagues in Italy and in China and Spain, and over the months, as this, it's like felt like a tsunami, right? Because you could see it sort of coming from afar. But in talking to them, it was clear that they were going to be on the precipice of maybe not having enough ventilators to take care of patients. And in Italy, that sort of actually happened. So that's what really brought this to the fore for this whole team to think about and to try to come up with a solution that might help our patients. We had a little discussion just before this about third world countries, and I hadn't really thought about this. Well, we thought about it, but just sort of peripherally. I would have thought maybe this could be used in third world countries, but as you said, Elizabeth, with your work in third world countries, that this could actually be used. Actually, be interesting to hear you tell us about what you found when you were in Vietnam and elsewhere in terms of the problems of not having enough ventilators.
Yeah, Art, thank you for that. So as someone interested in global health, I've spent some time around the globe in developing areas with a lot of incredible people and patients. And one of the things that I have seen, not during a pandemic, just during routine busy times, is the occasional patient having to be bagged by their parent, or perhaps two patients on a home ventilator or hospital ventilator. And so I was particularly moved and interested by your study. So from an infection prevention standpoint, what concerns or potential concerns exist when two patients may share this proof of concept ventilator? You talked about what the patients may or may not share and where the connections, where they connect within the expiratory circuit. But if you don't mind, just share as we think forward about whether this could be used in humans.
Well, I think the important thing is you have to have the same infection control measures, of course, for as you're dealing with a single patient. And I guess there'd be a temptation when you're monitoring or the medical staff, nursing staff, respiratory therapists are monitoring these patients. They're right beside each other, so it'd be a temptation not to take the same precautions. From the circuit itself, as I said, the circuit is only connected on the exhalation side relatively distally. The inspiratory lines are completely separate. So I think that the potential for infection is markedly decreased. I'm not an infectious disease expert, so I can't say that there's no chance that a little virus can track all the way back on the expiratory side from one to get back to the patient. I think that because the inspiratory limbs are completely separate, that should be much less likely to happen. One could argue that probably safest to have either two patients who don't have COVID-19 on this or two patients who do. have some sort of matching. Although I think and hope that the amount of contamination would be minimized because of where the connections are on the exhalation side. And of course, as I'm talking about, that's contamination through the circuits. There's still, as I started, contamination possible from one patient to the other by just the medical staff moving back and forth, et cetera. But that's not unique to this circuit. But it is unique, I guess, if you're using a single machine to ventilate, a couple of patients. Again, the interesting part here is the ventilator itself doesn't ventilate the patients directly. It's ventilating this bag in the box system. So any infectious agents that are in the inhalation side on the ventilator, they don't get to the patient. They get to the bag in the box system, which is quite a bit different. The other thing I actually forgot to mention, which I think I should, in terms of the system, that's interesting about it, is the ventilator is operated in pressure control mode. So it's a pressure mode of breathing. But the ventilation to the patients themselves is actually like volume control, because you've got a constant flow going through this fresh gas flow that I mentioned, and it's interrupted X number of times. So what happens during each of those breaths is you get a fixed volume that actually gets into the patient, subtracting away the gas compression, et cetera, that occurs in the tubing. So the ventilator itself is pressure control, but this is closer on the patient. If the patient, did measurements of the patient and didn't know where the ventilator was, you'd say, hey, this sort of looks like volume control, which is an interesting twist on this system.
Very interesting. Thanks. So you mentioned monitoring. How would you troubleshoot alarms with this system for those of us that are not engineers?
Well, one of the issues with using this is you can't use too many of the alarms on the ventilator. You can use one alarm, which we did, and that is if you looked at the exhaled volume, you could set the exhaled volume in the ventilator to be equal to the exhaled volumes of the sum of the two. And if one patient got disconnected, for example, that the ventilator would pick that up and set the alarm. But other than that, the alarms for the ventilator are not that helpful. You have to have alarms and monitoring that's independent for each patient. And in a lot of hospitals, that is going to be possible. They have extra sort of alarm sets that could look at pressures. You could even measure flow. You could measure exhaled carbon dioxide. You could have an oximeter on the patient. So you do all those things to monitor that specific patient. That wouldn't be possible probably not possible in third world countries. I doubt that all that hardware is sort of available. And then when something goes wrong, you have to be at the bedside and look at where things can go wrong. And usually where things can go wrong is where there are valves or T valves or T connectors where things can occlude. That's what you'd be looking for. One of the important things in putting this together, I think it's really important to put the circuit together well before you actually need it. It's like in times of crisis is not the time to say, oh my God, I just read this article and I'm going to go put this together and 5 minutes later use it on my first patient. I think that's a mistake. One has to think about it ahead of time, put the system together, run it as if there's a patient there, ideally with a test lung, because things that can go wrong, if you put the one-way valves in the wrong way, that's clearly a problem, right? And that's better to find that out on a test bench than the first patient you try. So I think a lot of the monitoring or troubleshooting is try to troubleshoot before you have a problem. In other words, before you actually put it on the patient. That's not to say things won't happen, but at least you're much better off, and much better off to have practiced with this, tried it a number of times before you actually do it on the first couple of patients.
Thanks for that. So it sounds like the optimal conditions would be obviously suboptimal, but the situation in which you don't have enough ventilators, but have adequate staffing and monitoring to be able to serve as that additional layer for these patients.
I think that's a great summary. That's absolutely correct.
Gotcha.
This is not a panacea. This is not, put the two patients, set up the circuits, put the two patients and walk away. That's absolutely not how to use this. It's interesting though. One of the things we tested, and it's in the paper, is if the patient, patient one or patient two, gets disconnected from the ventilator at the endotracheal tube, it has essentially no impact on the other patient. So, and that's not true if you just split the flow, split the pressure from a single ventilator to two patients directly, because if one gets disconnected from the endotracheal tube, the ventilator is essentially, it takes the path of least resistance or path of greatest compliance and ventilates the room. Here, if it's disconnected at the patient, that's not going to happen because the ventilator still ventilates the bag in the box.
So if I'm understanding correctly, compliance of one patient's lung does not directly or appreciably impact delivery to the other lung. Is that, or the other patient? Is that fair?
That's correct. It has essentially no impact. And we tried that in the test lungs with pretty divergent compliances. The test lung was set at a compliance of 10 mils per centimeter of water in one of them and 50 in the other. And actually, when you think about the disconnection means the compliance of that patient, the compliance is essentially infinite, right?
Right.
Because you're ventilating with one circuit, you're ventilating the room, which got a huge compliance, and it essentially had little impact, no measurable and no systematic impact on the other patient's flow, and that's because each circuit is pretty separate system.
That's really incredible.
Yeah, it's hard to visualize it. I think you're best to sit down. Anybody listening to this, just to repeat, pull out the circuit diagram, which is pretty straightforward from the paper. And when you're listening to this, I think that would be most helpful.
Has anything like this been used in humans, Art?
So we have not tried it in humans yet. We have tried it in a couple of pigs. And what we did to look at the difference compliance between two pigs, we used a pig that was, I think, 10 kilos and the other pig was around 40 kilos. So the compliance of one is about 4 times the other. And it seems to work extremely well. That's not the same, though, as using it in sick patients for, days on end when all sorts of things can happen that you may not think of in the animal lab or on the bench. It would be mucus secretions or fluid in the liquid or lots of things like that. So we're planning to do some of those experiments. As I mentioned earlier, we don't want to use it in our first 2 patients where we actually need it for those first 2 patients. We'd like to try it beforehand under really controlled conditions where we're really, really careful. But it hasn't been used as yet in humans.
Art, would you recommend to other centers to try to build something like this with the collaboration of their innovation, research, engineering teams in preparation for potential scarce resource allocation?
I think that's clearly up to each center. I don't want to make it sound like they have to do like we did, but I do think if they're at all concerned about the potential need, if they think they're going to run out of ventilators, essentially, then I think it's not a bad idea to sort of practice this. Most of the equipment, pieces and parts we found in the hospital without having to order it specially, but you might have to order some valves, PEEP valves. So I think if you're even thinking about using it, it's a good idea to try and set it up ahead of time. We've got on the website and the supplementary material, we have sort of a very detailed description of how to put this together. First of all, the first page is sort of the list of parts, and then there's pictures and step-by-step about how to put these circuits together. We're actually also going to put up, and I don't know actually if it'll be on the Society's website, a video of how we set this up as well. So I think that if anybody is interested in doing that, we'll provide as much support as we can to try and make it happen.
Great. Anything else you'd like to share about your work?
I think it's and we ended off the paper this way. I've been doing research for quite a while, and I can't. Almost every paper you publish or anything you do, you think, boy, I hope someone uses that because it's sort of everybody thinks their own work is interesting. Here, other than I hope that no one ever has to use it. I sort of view this as a bit of an insurance policy. Hopefully, we'll have enough ventilators around. Hopefully, we won't need them. Hopefully, this pandemic will come to an end. It's not going to happen very shortly, but it comes to an end, and hopefully, we'll need the ventilators. As you mentioned, the use in third world countries might be required, but it's one of these things that I hope never gets needed, and maybe it's just a great physiological exercise. But I think it is a cute way of doing things. This bag in the bottle system, which allows isolation. So I think that's probably how a reasonable way to end this and say that it should work, and hopefully it'll never have to work.
Great. Thank you so much for your team's contribution to science and to patient care, and wishing you the best throughout the pandemic and beyond. Thank you so much. This concludes another edition of the iCritical Care podcast. For the iCritical Care podcast, I'm Dr. Elizabeth Mack.
Elizabeth H. Mack, MD, MS, SCCM, is a professor of pediatrics and chief of pediatric critical care at Medical University of South Carolina Children's Health in Charleston, South Carolina, USA. Dr. Mack received her Bachelor of Science and medical degrees from the University of South Carolina. She completed her residency at University of South Carolina Palmetto Health and her fellowship at Cincinnati Children's Hospital Medical Center. She also completed a Master of Science degree with a focus on epidemiology and biostatistics at the University of Cincinnati. Currently, she serves as chair of the American Academy of Pediatrics section on critical care and is past chair of SCCM's Current Concepts in Pediatric Critical Care course.
Join or renew your membership with SCCM, the only multi-professional society dedicated exclusively to the advancement of critical care. Contact a customer service representative at 847-827-6888 or visit sccm.org/membership for more information. The iCritical Care podcast is the copyrighted material of the Society of Critical Care Medicine, and all rights are reserved. Statements of fact and opinion expressed in this podcast are those of authors and participants and do not imply an opinion or endorsement on the part of the Society of Critical Care Medicine, its officers, volunteers, or members, or that of the podcast commercial supporter.